All right, so welcome back, everyone. Hope you're all staying safe. And of course, the last few days was very difficult for all of us. My condolences for those of you who've been directly impacted. Personally, had a very stressful last few days. Seems like we are in better situation right now, but of course, stay vigilant and listen to, reliable sources and be prepared that if we need to leave and evacuate. Uh, as I said in my email, similar to other classes based on UCLA guidelines, we're going to have our classes this week on Zoom. Similar to what I said before, all the classes will be recorded. So if you don't want to, attend the class, it's not mandatory or required. Especially now, I understand some people may not be feeling well. So all the recordings will be available just in case. Another thing is for those of you who are not enrolled in the class yet, you're welcome to stay on Zoom. So there's no problem. I actually put it on the website and announce it to students to share with their friends because usually this time of year is when people shopping around and coming and talking to the professors about classes. Now with everything being online, it's much more difficult. Um, so it's probably a little bit more chaotic for like, enrolling in classes and all. But I'm gonna talk a little bit about the PTEs in the next slides actually. And the last thing is hopefully as you know, next Monday we're not gonna have a class. I think it's a holiday. Hopefully by next Wednesday, if the situation gets better, we're gonna be back in person. I think I made a joke last time in my class that hopefully we're gonna be in person unless something weird happens. And here we are. It's funny enough. My winter quarters always has something, sudden and unexpected happen most of the time. I think it started in 2020. So the first 2020 and 2021 was COVID. 2022 was okay, but 2023 was the whole encampment situation and all, and this year is this. But anyway, um, let's talk about the course and the lecture. This lecture is going to be about first some fundamentals, and then we're going to talk a little bit about cryptography. If you have questions, feel free to unmute yourself and ask the question. That's the easiest way. For some weird reason, I noticed that once people are on Zoom, they don't feel like unmuting themselves and asking, so they put it in the chat. It's not the most preferred option for answering questions for me because it's usually hard for me to keep track of the chat. But if you really don't want to unmute yourself and ask questions, feel free to ask questions on chat as well. I'll try my best to answer those questions. Okay? So let's get started. So as I said, I already talked about the lectures this week. Everything will be on Zoom, recorded. So we're going to talk about cryptography and some fundamentals. There are a lot of slides to cover. Most likely, of course, we're not going to finish it today. We're probably not going to finish it on Wednesday as well. What I'm going to do, since we missed the class last week, we're going to miss the class on Monday next week, is I'm going to continue recording the lecture on Wednesday and finish the slides. Of course, you don't need to stay in the class, but Wednesday lecture might be a little bit longer. Will be until the point that we're going to finish all the slides that I have, and this kind of counts as the missing lecture that we have. And again, everything will be recorded so you can watch it. Second thing is about enrollment. As I said, there are lots of emails about PTEs, and what's going to happen is that I need to wait until Friday because I want to make sure that the waitlist gets into the class, and waitlist is cleared on Friday. Starting Friday, I'm going to issue PTEs. And there are already lots of people who email me. They just reply on those emails, and hopefully I'm going to issue PTEs. One thing that can help us with this process is that if you're not planning to take this class and you're planning to drop it, please drop it as soon as possible so that people on the waitlist can get in, and then there are spots available in the waitlist. people can get in the wait list and so on and so forth. Okay. And then there will be the presentation list going out this week. Supposed to be last week, but all this crazy things happens and they postpone it. But I'm gonna post it on the website, so please check it and submit a Google form. The link will be there. Okay? Is there any questions so far? Yeah, go ahead, Aruna.
So just to make sure the waitlist will get accepted into the class.
Yes.
Okay, thank you.
Yeah, that's the main key reason that I don't issue PTs, because once I issue PTs, then they won't enroll people in waitlists. They don't enroll people on waitlist to the class. So the priority is people on the waitlist. So those people will go in first. Whatever remains, we're gonna issue PTs.
All right, thank you so much.
Yep. Any other questions? Okay. All right, so last time, if you remember, we talked about security principles. We talked about various different principles, threat modeling, overhead, multi-layer defense, etc., etc. We said that these are the main kind of ingredients of designing any sort of system. And any secure systems should follow these guidelines. And then we also talked about the fact that, unfortunately, there are bugs and implementation issues and some other things that ultimately cause the system to be not secure. Uh, to kind of give you an overview of what we're looking at in this class is that, as I said, we're looking at an IoT system as general. When we're talking about IoT system, and by the way, IoT systems also, there are other things. Uh, there are other names for it, such as embedded systems and cyber physical systems. Generally, we are looking at kind of a loop like this, where things starts with sensing. So there's usually some sort of a sensor because these devices typically interact with some physical world. Then the sensing goes through some form of a local processing and analysis. In many cases, kind of the loop closed here. So there is just sensing and some form of processing. Think about something like, I don't know, object detection or image detections, all those things. But in many, many other cases, the loop continues. So typically the local processing goes to the next level, which is the network. As the name suggests, these are internet connected devices. So typically there is some form of a connection to some other systems through some network. This network could be the internet, could be some local network, could be a combination of a bunch of other things. Given that there is this notion of connectivity, usually this devices are then connected to some edge device or some cloud device. These are more powerful computation systems that has more software, more hardware to do things. So many of the processing usually happens and quote unquote offloaded into this cloud environments. Um, and then at some point, the results will be usually sent back to the system, which will result in some form of an actuation. But as I said, usually an IoT system could be any combination of these five different ingredients. So there could be systems that doesn't have sensing, could be just local processing network or edge cloud. There could be system that's only local processing and actuation. So many of these different permutations of this five different ingredients is what happens in an IoT systems. In the most complete scenario, you have all these five different components in the system. Okay. Um, and as I said, not all the computers have all the components. Some of them has, just the sensor and local processor and so on and so forth. There are things that we need to concern about. In any case, there is, concerns about the software. There's concerns about the hardware, and there are of course concerns about the operating system in many of these systems. Um, and there is two set of interaction that's going on. And there is an interaction with the physical world, which happens through the sensing and actuation. And there's also interaction with the digital world, which usually happens through the network and internet and other sort of communication systems. Okay. So under this kind of model, the first question is, what is the threat model? What should we be worried about? What are the attack vectors? And the kind of the quick and simple answer to this question is that all of these above components, unfortunately, can be subject to an attack. So essentially, the threat model here is like, what are the attack vectors? And the answer to this, what are the attack vector, is everything is an attack. As we're going to show in this class, and this basically is kind of the schedule of this class, is we can start with sensing. We're going to show that how sensors can be fooled and how sensors can be attacked. We're going to talk about actuators as kind of also another type of kind of physical interaction and show that how they can be attacked. And then the rest of the class will be focused on local processing, cloud processing, and network, and how all of those components can be unfortunately attacked. So fortunately, this is a very, very wide kind of attack vector in terms of things that can be secured. And so what is the status quo given this system and this complexity? Unfortunately, the news and the kind of the key situation at the moment is that we didn't mostly care about security in such a system. Why? There are three main reasons. First is we didn't really design systems for security because security wasn't really the main objective in our systems. Why? Because of multiple reasons. One is because there are other metrics in the systems that are more important and more time sensitive. Uh, Things such as functionality, performance, power consumption, and so on and so forth. Second thing is more of a negligence and lack of knowledge. Many of these systems are designed by people who are not expert in security. So there's just naturally, it's not their main concern that, a system needs to be secure and so on and so forth. Um, and as a result, we are kind of in this situation that we didn't care about security and it's kind of now is coming back and hurting us significantly. So, and what happens is that in the past 10 or 15 or 20 years, we have realized that this was a very, very wrong approach. And unfortunately, now it's kind of too late in many systems. That's why we are observing and witnessing lots of these attacks that is happening, and it's kind of causing a lot of problems and costs for the systems. And what we need to do now is kind of like two things. One is kind of trying to figure out what we can do with existing legacy systems and hopefully can learn from this and design systems for future that are actually secure. The current strategy is for this legacy systems is kind of a whack-a-mole systems, right? Like something pops up where you can quickly realize what the source of the problem is and where to fix it. It's kind of like, the fire situation here in LA, right? So it just mainly didn't care and something happens and now it's just trying to put it out, right? So it's kind of like the same strategy with cybersecurity, honestly. And then of course the next question is what is the future trend? So are the things getting better or worse? And should we care more about security, less about security, and so on? The answer to this is there are two major trends that cause security even more important. Number one is that there's going to be more devices in the next decade or so. This is already what we are seeing, but we're going to continue to see this. And kind of talked about this in the introduction lecture as well, which basically many things that used to be not smart and not connected to the internet and so on are now connected to the internet, which means that the attack vector is now even bigger. This is mainly fueled by cyber physical systems and Industry 4.0, which is kind of like, automating everything through computers. And these are some numbers for you, like 200 billion devices by 2020, which already passed that. $11 trillion business this year. And the second thing is that, as I said again, this is something that I discuss in the introduction lecture, is that they're just more security critical applications, right? So it's more difficult. So there are more devices and they're controlling more critical systems. So that's why it's much more challenging to secure those devices in the next decade. Okay. So with kind of this kind of quick intro, kind of relevant to what we discussed last time, let's quickly talk about how do we build a secure system. And then this would be kind of like the bridge to the first kind of main topic of this course, which is the cryptography, which is kind of the main ingredient of building a secure system. Okay. So the basic idea of building a secure system is that uh, uh, we should let the control to something that we trust, right? So the kind of the basic idea of building a secure computer system is that the control of the system should be based on something that we trust. Okay. So now the question is, okay, what do we trust? We kind of uh we there are different options for this and there are different solutions for this. But typically we trust something that is uh we kind of manually checked and goes through a very rigorous process. And it's very, very hard for an adversary to tamper and modify. Uh, and this thing is what we want our system to be built off of, right? So this kind of like is what we call the root of trust. And everything else we want to kind of control it by this or somehow kind of gradually build on top of it. That's kind of the basic idea of any sort of secure systems in cybersecurity, though. So what are the candidates? Are there software or hardware? Both, as I said, it's kind of combination of both. We typically trust in hardware easier because hardware is this kind of tied to physics. And since it's hard for the adversary to, let's say, change the physical attributes of the system, typically we can trust kind of like the actual physical attributes, including like the actual physical logics and transistors and memory and all those things. Because it's very, very hard for adversary to change that. Because that requires an intrusive change of like, physically going and moving the, pins and connections and so on and so forth. Interesting thing is that unfortunately, this is also what like I could have said this very, very confidently 10 years ago, but there are very sophisticated attacks that's also kind of trying to attack this system. But still, it's quite common to trust the hardware in many, many cases. Okay. Can we trust so now that we kind of like trust the hardware, the question is that would that be enough for us to build a system? The answer to that is that we wish if we could have had a very small piece of hardware that controls everything and give us all the functionalities that we needed, that would have been great. But unfortunately, for those of you who have done any sort of hardware design, any sort of complex applications such as scheduling or interacting with I/O and all those things is very hard in hardware. That's why we kind of rely on software for these things. Typically, we add these other layers such as the operating system and firmware and so on. On paper, your operating system could be baked into the hardware, and that would have been very, very secure. But again, like building these things in hardware is very costly and very inefficient and error prone and so on and so forth. That's why we need to rely on software. Okay? And then so now that we kind of see the software, your big question is, can we trust software? And the answer to this is unfortunately most of the time no, right? So that's kind of like why we are in this kind of very complicated situation with cybersecurity because we need to rely on software and most of the software we write is not very secure. Why? There are two things that kind of prevent us from trusting fully in software. Number one is the bugs. Most of the software that we write are very complex, thousands and thousands of lines of code. So it's very hard to kind of like follow specific guidelines or kind of manually check for bugs and all those things. Of course, there are tons of these different, tools and algorithms for formal methods for checking and testing. Those of you who are more uh, familiar with software engineering probably have seen these, but you probably have seen this almost inevitable and impossible to write software without bugs. That's number one. The second problem with software is that things gets a little bit more dicey when it's to start to interacting with outside world. We're going to talk about things such as buffer overflows or return-oriented programs and so on and so forth. These systems, if they didn't interact with the external world, they would have been fine. But unfortunately, since they need to read and write from the I/O or memory and so on and so forth, they actually, like the bugs kind of show up there. So many of these systems, without those interactions, even if they were still buggy, there wouldn't have been much problems that we are seeing now. Okay? Okay. So let's take a step back. I told you that in order to trust the system, we need to build the trust off of something that we know and trust. We said that do we trust hardware? And we say mostly we are. Do we trust software? Mostly we don't. Unfortunately, though, that we need software to control a lot of things, so we need to kind of figure out a solution. Uh, and then, of course, when we are kind of like, don't trust this, and the university takes, control of this, unfortunately, what will happen is that they take control of the whole system, and in most cases, kind of game over. So what do we do? Excuse me. What do we do is that the current approach in most of our systems is that we have this smallest things possible, which we call the root of trust, okay, or ROT, okay? What is this root of trust? This root of trust is something that we build very, very carefully. Usually it's a combination of a very small hardware and very, very tiny piece of software running on top of it. There are a whole bunch of different kind of controls and checks and balances that we put there to make sure that the system cannot be modified and it's very well isolated and so on and so forth. Okay. We then kind of boot our systems into this root of trust, and this will give us what we call a good known state. That we know that, at least at the beginning of the start of this system, we know that the only thing that runs on this system is the root of trust, and root of trust hopefully is not being modified, which is kind of like a true statement in most cases. And then we take the control, like we give the control to root of trust, and then we have a mechanism for building the root trust on top of the root of trust. How does it work? So as I said, it's just kind of like, we build this trust gradually. What happens after, like, after that good known state is that unfortunately the system needs to interact with real world. So it's kind of like a Wild Wild West situation that, anything could happen. And then again, this would be a story of this class that we're going to talk about, that the systems that it is correctly and securely boots to a non-good state. But unfortunately, as it starts interacting with the rest of the world, bad things going to happen. And then what do we do for mitigate that? So it's not like, we are kind of completely helpless. There are various different things that we do, and we're going to discuss also in this class, including isolation, verification, monitoring, better design, design for security, and so on and so forth. So we're going to discuss those things for those other components, including the sensors and actuators and so on and so forth. Okay, so I told you that there's something that we trust, and that is our root of trust. And I said that mostly hardware based. What is that exactly? Um, as I said, the kind of like the principle that we are following. Remember that I told you the simplicity is one of the main principles. So we need to build something that is not easy to modify, read, or change. And this is usually referred to as what we call a trusted platform module, or TPM. Uh, there are other names depending on the manufacturer and the vendor. Some people call it enclave and so on and so forth. Um, but essentially the idea is that the trust starts here. Okay, so the trust starts in TPM, and everything else is built on top of TPM. So once we boot the system into the TPM, and it follows a process called a secure boot. Then TPM has some functionalities, security-oriented functionalities, and then hopefully at some point it will then securely boots the rest of the system, including all the other components and the operating systems. It will then pass the control to the operating system, and then the operating system will then start doing activities. Questions, Jacob?
Yes. What's the difference between the ROT, the root of trust, and the TPM? Is the TPM like a root of trust?
Correct.
Okay.
So root of trust is a concept.
Mhm.
Is the very first thing that you trust. There is nothing below root of trust that you trust, right? So this is like the first thing that you trust. And a common way of root of trust is TPM. Does that make sense?
Yes, thank you.
Mm-hmm. Okay. So the question about TPM is that what are the functionalities needed for TPM? There are multiple things that we need in TPM. First, we need some form of a memory to hold some secure code. And this memory has to be private and isolated, should not be exposed to the rest of the system. Because remember, we want something that the adversary can no way kind of read or access or change things. So everything has to be kind of like physically isolated. Okay. So we need some form of an internal memory within TPM. The second thing that we need to do is some functionality to verify the status of the system. Because remember, this is the root of trust. It needs to be kind of verifying that some other part of the system to make sure that these other parts are also not being modified. And then we kind of like gradually increase the level of trust that we have in system. And in order to kind of do the second bullet point, we need some ability to run some basic stuff, right? And this is usually some cryptography functions that we're going to talk about in this lecture. So there is a big trade-off here is that what sort of functionalities do we want to run? What sort of capabilities TPM has? Remember that although we want to have, very powerful TPM with many different functionalities, that is directly in contrast with the simplicity requirements that we need to have. So as a result, we're going to kind of have a very minimalistic approach. We want to have the TPM to be as small and as simple as possible, such that it runs bare minimum that can gives us security. So we don't want to have like a sophisticated, like very complex processor as our TPM because that kind of defeats the purpose. We want to be something that's small enough so that manually can be checked and like transistors can be checked and so on. So, question, Tayu.
So I guess the general question is the TPM like some component on the chip or
Yes,
okay,
it's an actual hardware components. Yeah, it's a chip.
I see. But I thought like computers booted from the hard drive because they needed some form of persistent storage. So you said earlier that the TPM or that computers boot from the TPM or it's like
Yes, I'm gonna
oh,
show you in the like I think in 2, 3 slides so what the secure boots looks like. So eventually it gets into the hard drive, but before that there is actually boot into the TP. Okay. So as I said, some cryptographic functions and some activities for checking various things. That's the main part that we're gonna actually talk about in this lecture. But before getting to the details of cryptography, I don't know what happens to this part of my. Oh, okay, there you go. Before talking about cryptography, let's actually finish the secure boot. So let's say for now you know things such as hash functions and encryption and so on. We're gonna talk about them, so don't worry if you don't. But generally, this is how the secure boot will work, okay? So once you like turn on your computer, the first thing that happens is that the TPM gonna run an initial code that stores there. So there's literally a piece of code that is stored in TPM. The first thing that happens is that that code will run, okay? The next thing that happens is that the TPM will start reading the insecure memory, okay? And that unsecure memory is what's been read from the hard drive, as one of the students mentioned, Tayu mentioned. So TPM going to start reading the hard drive, and it's going to verify the piece of code in hard drive that needs to be running next. For example, the boot sequence for your operating system. There's various different things that needs to run one by one. For example, the driver needs to be loaded, the interrupt service routines needs to be initialized, various different function calls needs to be initialized, the scheduler needs to be started, and so on and so forth. There's this kind of layers depending on the type of operating systems that we need to run. There are these things that needs to be running. What happens is that the TPM checks the first kernel. It verifies the authenticity of the first kernel of that code. And then that kernel will be run next. And then that kernel will check the authenticity of the next kernel, and that kernel will run, and so on and so forth. Okay. How do we check the authenticity and so on? We're going to talk about cryptography first and then come back to the slides next week, hopefully. But basically, this is kind of like the process. So there is this TPM that we do trust. We don't need to verify anything from it. It has a piece of code and it has some functionality that can run this code. It will run this code, and what this code does is that there is this big memory system hard drive that you have. There is at somewhere in this hard drive, there is your kernel, okay? And as I said, this kernel itself is layered. So there are different functionalities within this kernel, okay? So what it does is that it checks it verifies the hash function of this code, make sure that this code hasn't been modified. If this code hasn't been modified, then what it does is that it lets the processor to run this piece of code, okay? Since I know, excuse me, since I know that this code hasn't been modified and this hardware, the CPU has been initialized correctly, now I can securely run this in this, and then this is also now trusted. And then, as I said, this is kind of like usually chain, which means that this piece of code checks the authenticity of this piece of code and authenticity of this and this and this. Eventually, this kind of like the steps will run, and at some point, we're going to have the full operating system fully loaded into the system. Okay. At this point, we give the control to the operating system. The operating system then gives the capability to the user and start interacting with the user to get the commands and run different applications and so on and so forth, right? So this is what we call a good known state. This is where we trust, we're happy with this. But unfortunately, after this, since there is interactions with the user through IO and other things, that's when things are getting insecure. Okay? Any questions at this point? Perfect. So there's also a whole bunch of things that we do at the operating system level, including isolation, re-verification, OS verification, monitoring. So it's not like, once, the control is passed to the operating system, we don't do any checks. But unfortunately, this is an ongoing battle between the security, the attackers and defenders and designers and so on, which we're going to talk about. Okay? And then of course the question is, what if the system doesn't have an operating system? Okay, question, Aruna, go ahead.
Yeah. So for the previous slide that you talked about, where like you iteratively, like I guess, verify that the code is secure, is that sort of like a TCB, like a trusted computing base, I believe?
Well, yeah. So the trusted computing base is essentially, so the kind of the terminology is that you have a root of trust, which is kind of the hardware and software that you trust. Then initially, as you kind of like check the authenticity of these codes, this is going to be added to your root of trust. Then this is called TCB, or trusted computing base. Okay. So this part is a static TCP. So this is the static part that you initially trust. As you add these things, this becomes part of your dynamic TCP, that you add more and more things as the trusted part.
Okay, thank you. Yep.
How are you?
You also mentioned that the OS needs to do at some point like to load drivers and interrupt routines. So is that done by the kernel or is that done by the TCP?
No, so it's not done by TCP. TCP only checks like a very basic kernel. Afterwards, since very first functionality within that kernel, okay? Once we trust that, everything else then done by that. The reason that we don't want to run everything here is that then we need to store everything in this memory, and this memory is small, okay? The reason that you need to have some form of a chain-based dynamic system is that you don't want to put everything in your TPM because you have limited, resources. You want to kind of do this kind of step by step, that TCP only trusts one kernel, but we have a mechanism to expand that trust using cryptography and using the CPU.
That makes sense. Thank you.
Yes, and then the final thing is, what if the system doesn't have an operating system? In that case, then instead of like loading the kernel, you either directly load the software that you want to run, or if there is some form of a lightweight operating system or some form of a firmware, then you load that system. There are systems that then necessarily doesn't have like a very involved secure boot. That's also another possibility. Okay. But we're going to talk about this a little bit more. If you're interested in kind of the secure boot and how all these systems are stored securely, actually I included links for almost all four kind of major device manufacturers, including Intel, Google, Microsoft, and Apple. Take a look at these links. They're very useful. It's kind of repeating what we were saying, but a little bit more details about them as well. Later in the class, we're going to also talk about various forms of TCBs and more advanced options, including trusted execution environments and what are they. Because the idea of TPMs and TCBs is not just for the secure boot, it's actually you can extend it throughout the execution of software. And that's where we're going to have environments, which we call trusted execution environments. So a good portion of this class is going to be about those as well. But for now, we're going to use TPM for just securing the system. Okay. Before going to the cryptography, last thing I want to say is I told you that we can trust hardware and we can trust TPM. Unfortunately, as we're going to show a few examples later in this class, is that that's also not true anymore, given that the adversaries can show and change some part of the hardware. So we kind of had this very weird situation right now that some of the things that we thought that it's going to work is not working. Sometimes it's working, sometimes it's not working really. And again, this really depends on the threat models of our systems. And again, that's why, although we think that our systems are secure, in many cases are not, and all these attacks happening. All right, to summarize kind of things that we said so far is we start the trust from some base. We kind of then have a mechanism to kind of expand this trust. Unfortunately, this gets quickly out of control because we add more complexity to the systems and layer of software, and these layers of software are buggy and interact with the physical world. But in some cases, it also works. So it's not always like kind of, it doesn't work all the time. Another problem that we're going to face is that hardware fully cannot be trusted. And this is something we're going to show through side channels and different types of attacks in this class. But generally, just keep that in mind that we start with this small piece of hardware and software and gradually add things to it through cryptography. Okay? And as I said, it's not just about secure boot. We also have other measures to at least fix this issue if something happens. So we have methods for detecting and mitigating issues. So part of the security research is not just about how to make the system to start securely. It's also about if something happens, what can we do and how we can salvage the system. Okay? So let's talk about crypto. Is there any final questions about this part? All right, so let's continue for like 10, 15 more minutes and we're going to have a quick break. Okay. So a few things I want to say before getting to the details. I'm just going to go over the concepts and ideas mostly. A bit of implementation as well, but not very detailed. So this is mostly very informal discussions on cryptography because cryptography is one of those areas, unlike other aspects of computer systems, that's mostly I would say not grounded in theory. Cryptography is very, very grounded in theory. Um, but we're not going to talk about the theory aspects of this in this course because we don't have time, and this course is a very system-oriented class. So you need a separate and very complete course about cryptography. There's actually very nice courses here at UCLA, including CS 136 and 236 and 282A and B. UCLA also is very famous actually for their cryptographers. They're very famous people here, especially in the CS departments that have done lots of numerous great contributions to cryptography. So I would definitely recommend consider taking courses in this domain. But the purpose of this lecture is to give you kind of like a brief introduction to cryptography so that if you never had any exposure to them, you at least understand the basics. It will be a little bit confusing at first. So don't be afraid. Also, there will be some formulas and some math. And then this will be the last time you're going to see some math and formulas in this class. But I think it will be helpful to kind of learn a little bit of that. So yeah, let's continue with that. So, but I would definitely recommend you to kind of explore a little bit yourself and read, books and all if you need more details. All right. So what is the foundation of cryptography systems? What is the main theory behind many of these things that we're going to discuss? Typically, we are kind of roots the security of our system based on some assumptions and definitions. And then based on this basic assumptions and definitions, we have mathematical means to prove them, okay? For example, there are some known NP-hard problems. And then what cryptography do mostly is showing that if those NP-hard problems are indeed NP-hard problems, there are ways to show that this problem reduces to that problem. Okay, so for example, decryption of a cryptography algorithm eventually leads into solving an NP-hard problem, and since we cannot solve that, then our systems are secure. So the kind of like the basics of many of these things that we're going to discuss is based on that. Okay, so just keep that in mind. Again, for those of you who don't know anything about algorithms and hardness of problems and so on, don't worry about it. We probably want to kind of quickly check it, but it's not something that we're going to actively ask you in this class. Okay. All right. So a very, very high level of a crypto system is a system with 4 different components. There is a secret value, which we usually call key. Sometimes it's a pair, sometimes it's a group of things, sometimes it's multiple, sometimes it's just one. But typically there is at least a secret value. Then there are 3 other things. There is a cryptography algorithm. This algorithm could be encryption or decryption or message authentication or hash functions or combination of various different things. So there are many, many different algorithms for many, many different functionalities. And then, of course, there are inputs and outputs, okay? The inputs, depending on the system, could be a message or could be code or data, whatever. And the outputs usually the ciphertext or hash and so on and so forth. The biggest thing about a crypto system is this Shannon or Kirchhoff principle, that the crypto system is secured if everything about the systems except the key is known to the attacker. Okay, so the attacker will know and should know everything about the algorithm. In many cases, the attacker knows the input and the attacker knows the output and still cannot find the key. Okay, so that's what we want to achieve in the secure cryptography systems. Of course, the specific assumptions depends on the system. For example, in some cases, you may not know the input or the output. But generally, a system is secure if everything about the system except the key is known to the attacker. It's not a good idea, as I said last time, that having an obscurity in the systems. For example, you cannot rely on the fact that your algorithm is semi-unknown to the attacker, and your security of your crypto system should not be coming from that fact. Okay? So there are various different, so based on these kind of like basic assumptions, there are various different primitives. We're going to discuss these primitives in this class. These are kind of the main basic blocks of a cryptography system. The very common ones are encryption and decryption systems, which further can be symmetric or asymmetric, as we're going to talk about. We're going to talk about secure hash functions. We're going to talk about message authentication codes, and we're going to talk about digital signatures. These are the main things that we're going to talk about in this class. But there's a whole bunch of other things that build on top of these primitives, such as identification, zero knowledge proof, key exchange, TLS, which is used extensively in internet systems, multi-party computations, secret sharing, smart contract, blockchains, and all those things. These are protocols that build on top of this primitive. So what we're going to discuss in this class and this lecture is this 4 primitives. Based on this, then you're going to learn a little bit about these other things later on in this class or beyond this class, actually. Once you learn these basic things, then you can build those higher level things, okay? All right, so let's start with talking about encryption, decryption. That's the kind of the most common things that you see. The terminology that typically we use is that encryption an encryption algorithm is usually shown by, capital E, which takes 2 inputs, the message and the key, and you produce an output called ciphertext. And decryption is the opposite of that. It takes the ciphertext and the key, it decrypts it and gives you the message. If this key and this key is the same, we call this a symmetric encryption system. If this key and this key are different, we call this an asymmetric. We're going to talk about both of them. We're going to start with symmetric systems that use the same key. Then we're going to later on talk about asymmetric, probably today or maybe on Wednesday. Okay. So what are the main properties that you're looking for in encryption decryption systems? The main property that you're looking for is correctness. Essentially, the idea of correctness is that if I encrypt a message and decrypt it, I should get the same message. If I receive a different message, then it doesn't matter whether the system is secure or not, it's not useful for any systems, right? So if I don't receive the same message that I intended to encrypt after decryption, then this is not a good cryptography system. Okay, so correctness is the main thing for any crypto system, is any encryption decryption system. There are additional options that some systems have. For example, I'm giving you an example here called homomorphism. Homomorphism is basically saying that if I have a function, this could be any arbitrary functions, for example, let's say addition, okay? So if I apply a function to two inputs, M1 and M2, if my encryption system has homomorphism, then I'm going to have this thing that f of M1 and M2 is equal to, if I encrypt these messages first, apply f next, and decrypt the function afterwards. So let me give you an example. F is actually addition, okay? So what does this mean? This means that if I have addition, let's say I have two messages, M1 and M2, I'm going to add them in the plain text domain, in the regular domain, and I'm going to get something like X, okay? So for example, let's say this is 3 and this is 4, I'm going to get 7, okay? So the idea of homomorphism is that if I encrypt M1 and get C1, and if I encrypt M2 and get C2, then if I apply the same F, in this case, addition, so basically I add C1 and C2, and let's say I get Y. And if I decrypt this Y, I'm going to get, let's say, Z. The idea here is that this Z should be equal to this X. If this Z and X are the same number, excuse me, then we call this, it has homomorphism over the function F, in this case, addition, okay? Why homomorphism matters? Because homomorphism means that I can then apply things in the encryption domain, which is very interesting in many cases, including privacy preserving and all, which if you have time later in this class, we're going to talk about them. But the main thing I want you to focus on for now is this correctness property, that if I encrypt something and decrypt it, I should get the same message, okay? So let's talk about what is a secure algorithm, like what is a secure encryption algorithm? And I want you to think about it a little bit and give me some answers. Like, what is a secure encryption algorithm? Like, what are the main things that we are looking for in encryption mechanism? Or let's ask this differently. Like, if you want to attack an encryption algorithm, what is the first thing you would do? Anyone wants to answer this? Jacob.
You could try to guess how to break it, like just guess the key.
You should guess, like it should be hard to guess, right?
Yeah.
So like a secure algorithm should be very hard to guess the key. Or maybe even not the key, maybe just let's say I have a message and I encrypt it. It should be hard to guess the message, right? So it should be very hard for you to know what was the original message that's being encrypted. That's good. Anything else anyone wants to add? No one wants ever
Maybe
wrote.
also I'll add. Oh, see
Yeah,
someone
go
else.
ahead.
I was also gonna add like it should, like your encrypted data should be random. It shouldn't it should have no patterns. I guess that's kind of related to what you already said, where you shouldn't be able to decode the message, but it shouldn't be related to the message.
Yep. Alec?
So it should be easy to do it normally, as in like if you have the key, but it should be like really difficult to not, because if it's hard for you as well, then it's not really usable.
That's a very good point, yes. And this is more of a for the usefulness or feasibility of the approach. So it's not just about security, it's also, as I said last time, security also should be something that should be user-friendly, and that's a good point. Tayu?
Maybe it should like still look random. The output should still look random even if you do it for very large, like plain text. Like
Yeah.
doing it more shouldn't make it seem more like a message.
So I think it's also kind of what Jacob was also trying to say, that it should not have any patterns, like recognizable patterns, and that's a good point. Good. I think that's great. So yeah, so I think what all you guys said is correct. I'm going to give you a little bit more formal definition of what is a secure algorithm. Before that, I want you to kind of give you some examples of sort of attacks that can be done. For example, a very famous attack is what we call frequency analysis. So consider, for example, a method that I just substitute every character in English with some other characters, like, A to E or B to Z or whatever. So I just permute things and randomize things, and I consider this as kind of a secure encryption mechanism. In fact, this is not secure. The reason for it is that I can apply a well-known frequency analysis attack to it. Essentially, the idea of frequency analysis is that for a very long sentence, the distribution of characters is something like this. So, for example, people have shown that E is kind of the most common characters used in English language, right? And then there's others such as A and T's and so on and so forth, right? So what I can do is that if you have some form of this like semi-randomized mapping between characters, what I will do is that even if let's say I cannot, for example, if you write ABC and becomes easy, I don't know, like T or whatever, even if I don't understand what this says, what I'm going to do is that I'm going to run the same frequency analysis. I'm going to see that, for example, instead of E becoming the most common word, I'll see that, for example, for another words, another character becomes the longest or the most common one. And what happens is that I can say that, okay, this should be then E, right? So I'm going to like find a one-to-one mapping based on this frequency analysis. And I'm going to be able to basically kind of like reverse engineer the mapping that's been used to encrypt the system. Okay. And this is actually quite common. It's been used in this system called Enigma machine. That's been used in World War II. For those of you probably familiar with Enigma machine and Turing, Alan Turing, which was the guy who invented this kind of attacks to this to this Enigma machine. That was kind of like what happens at that time. We're gonna have a project for you that you're gonna actually try to also kind of do this frequency analysis and figure out an attack. But generally, this is a very common practice. So your system should be kind of like secure against this. And as I said, in the next slides, I'm gonna show you the more formal definition of why this should be secure. Frequency analysis is not the only attack. There are other attacks such as brute forcing, differential, cryptanalysis, and so on and so forth. Those of you interested in these kind of like breaking crypto, there's a large body of work on that. But let's actually define what is a secure algorithm. So a secure algorithm, an encryption algorithm, is an algorithm that should be very hard to completely determine M from C without the knowledge of K. Okay, so a very simple definition that if I see C but I don't have K, it should be hard for me to determine what is M. Okay, what is the message? So there are some thoughts that you need to think about. Then, as you can see, for example, my wording says completely determine. So there is some notion of partial versus full. For example, is it okay if I partially understand M from C or not? In most cases, we don't want that, but in some definitions, you can also say that maybe it's okay to partially understand M, but not fully, okay? The second thing that you need to pay attention to is the attacker's capability. And again, remember last time I told you that anything that we want to consider the security of, we need to consider the attacker's capability. there are three main things that usually we need to consider. It's called ciphertext only, known plaintext, and chosen plaintext. Ciphertext only is like the weakest model. The assumptions about ciphertext is that the attacker only knows ciphertext. So there's like a big group of ciphertext that the attacker has access to, but nothing else. Known plaintext means that the attacker has pairs of M and Cs, some limited pairs of M and Cs. So not only the attacker knows the ciphertext, but also knows the message, some of the decrypted version of that message. Okay, so let's say somehow the attacker breaks into some system and found some limited pair of M and Cs. Okay, this is what we call a known plaintext. And lastly, the attacker can have chosen plaintext, and this is the strongest attacks. The idea of chosen plaintext is that the attacker has access to some form of an oracle, that they can choose any plaintext that they want, and then they can choose a ciphertext that they want. And this chosen plaintext can also be chosen ciphertext, okay? Which means that the attacker can choose the ciphertext, and they can decrypt it at will. And we're going to talk about that as well later, okay? So under these assumptions, we want a system such that it should be at least CPA secure. It means that it should be chosen plaintext secure, which even if the attacker can choose which plaintext they want to see and the corresponding ciphertext for it, still the system should follow this kind of definition above. Okay. So let's actually go a little bit deeper into this. So as I said, the definition is kind of like vague, and the idea is that if I, for example, find one bit, if I, for example, know whether M is even or odd, would that consider a secure system or not? Or is it just only knowing completely what M is the notion of security? Okay. So this is what we want to achieve in most cases. Essentially, what we're trying to achieve is kind of a slightly different definition of a secure algorithm, encryption algorithm. Say, for example, we have two messages, and what happens is that there is a ciphertext. Then we say that this system is secure if the adversary cannot guess better than 50% whether this is M1 or M2, okay? And then to kind of make this even more generic, we're gonna define what we call perfect secrecy. And perfect secrecy is defined like this, that for all M0s and M1s in the message domain M, let's say, for example, your message domain is every word in English language, okay? Then for all Cs, for all ciphertext in domain C, and a random variable K, which is the key, which is uniformly distributed in some domain K, then the probability of seeing C belongs to M0 should be exactly equal to the seeing C coming from M1. In other words, for every single pair of messages, okay, if I see a ciphertext, I should not be able to tell which message this is more likely that ciphertext coming from, okay? This is what we call perfect secrecy, and this is kind of the gold standard in encryption mechanisms, okay? Essentially what it says is that if I see C, I have no idea which message is this. I cannot tell that there is a group like even or odd or single bit difference. It should be uniformly distributed in the message domain, and should be equally likely that any message will result in C. That's what we want to achieve in a perfect secret encryption algorithm, okay? So now the question is, can we achieve perfect secrecy? The kind of the semi-good news is that yes, we can. And surprisingly, achieving perfect secrecy is very, very simple. It's using this algorithm called one-time pad or OTP. And all it does is that it's just XOR the message with some secret key, okay? And the funny thing is that people have shown that the only thing that you need to do in order to achieve perfect secrecy is that you take your M, your message, You XOR it with the key same size. Has to be same size, and that's a big thing. You're gonna get the ciphertext, and this ciphertext is gonna be uniformly distributed. As long as this M and K are uniformly distributed, this C will be uniformly distributed. And that's the main thing. And very simple encryption algorithm, but it achieves perfect secrecy. So there's no way that you can, detect anything from C without knowing what K is. Okay? So with this, the encryption is very simple. As I said, encryption is basically XORing M with the K. Decryption is also very simple. The decryption is also the exact same operation. It's basically XORing C with K. The reason for this is XOR is a reversible function. Essentially, if I show C as M XOR K, and then this XOR with K again. So I'm just substituting C with M XOR K. XOR, so what I can do is that I can write this like this. And what happens is that anything XOR with itself will result into 0. And anything XOR with 0 is equal to itself. So the results of this will be equal to M. So that's why if I take the ciphertext XOR with K, I'm going to get M. And remember the correctness property that decryption of encryption of M should be equal to M. And that's exactly that, right? So encryption of M is M XOR K, and decryption is XOR K again, and this is equal to M as I just showed. Okay? So very simple encryption algorithm, OTP, one-time pad. All you need to do is that you have a key that's uniformly distributed in the domain of K. You XOR it with your message, and boom, you get all you want. So question is that if OTP is this simple, why do we need to learn a lot of things from cryptography? There are two major problems with OTP. The first problem is that the key K needs to be same size with the message, okay? This seems to be not an issue for small messages, but what happens is that think about practical cases that you want to, let's say, encrypt your entire hard drive, gigabytes of data. What this says is that essentially your useful storage size is divided by half, divided by 2, because essentially for any message of size X, you need another X for storing key. So essentially anything that you want to store, half of it should be for the key. And also think about the way that we need to kind of communicate this key with another user and so on and so forth. So communication is also becomes a big issue because in order to decrypt, somehow this key has to be transferred. And now if I want to encrypt gigabytes of data, I need to transfer somehow this gigabyte of key to another user. So there's a whole bunch of these computation and communication storage problems for a very large key. Ideally, what we want is we want our message to be really large because we want to be able to, encrypt and decrypt gigabytes and megabytes of messages. But I want our key to be very small. I don't want to scale the size of the key with the size of message. I want to have just 256-bit that can magically encrypt and decrypt terabytes of data. That's what we want in a realistic system because that way the only thing I need to transfer is the data, and transfer data is simple because I can encrypt and decrypt it. I can somehow figure out a way for key, for a small key, like a few bits here and there, hundreds of bits here and there. But I don't want to be able to transfer gigabytes of data. So that's one big problem with one-time pad. Then unfortunately, the key size needs to be as big as message. The second problem with one-time pad is actually the many-time pad. So one-time pad is secure, but two-time pad or many-time pad is not secure. Why? Because if I encrypt the same message twice, so for example, let's say I have key K1 and I want to encrypt yes. What I would do is that I make yes into some, let's say, hex number or some bits, Then I'm going to encrypt this bits and this bits, using XOR, and I'm going to get ciphertext 1. If I do this again and again, if I encrypt, yes again and again with the same key, I'm going to get the same exact C1. Never going to get a different answer, okay? Why this is a problem? Because remember I told you that the adversary should learn nothing about the message. For example, let's say the adversary sees this. Sees four consecutive C1s, and then after some point is C2. This will mean that the adversary can know the pattern of the user. And let's say, for example, for some cases, the adversary knows exactly what C1 corresponding to. So basically, all I need to do as an attacker is that I never break the system, but basically by seeing the repeat of the same pattern, I can say that, oh, the same thing happened. So it means that the users keep saying yes to the questions. So this is what we don't want to have. What we want to have is what we call a probabilistic model, which if I encrypt yes, each time I'm going to get a different C. So one time I get C1, the second time I get C2, the third time I get C3. So what the adversary will see is something like this. And the adversary has no idea that I'm actually encrypting the same message. Of course, you might ask that if C1 and C2 and C3 are different things, how the hell do we gonna encrypt this and decrypt this? Because then this seems to be a different answer each time, so it's not gonna have the correctness. And we're gonna show you how we're gonna actually do this with some tricks that we're gonna introduce later. But we want to have a system that, first of all, the key is very small. And second of all, we can encrypt the same thing multiple times, each time results in a different ciphertext. These are the very two important things that we need to achieve. Before continuing, let's have a quick break because Zoom might be difficult for people to follow along for a long time. So let's have like 5-minute break. We're gonna come back at like 5:16. Okay? All right, let's continue. Okay. So let's focus on the first problem. So as I said, two problems. One is the size of the key should be size of the message, which we don't like for visibility purposes. And second question is we want to have a system that generate different ciphertexts from multiple different times of encryption. So essentially we want to have a secure two-time pad or many-time pad. Okay. So what should we do to fix the first issue? What we need to do is that, people realize that perfect secrecy might be a little bit too much. This might be an overkill. So they're started to think about relaxing perfect secrecy. And that's when this very famous thing called semantic security came along. It came along. So the idea of semantic security is very similar to perfect secrecy with just one simple difference, okay? So in perfect secrecy, we had two messages and they were universally distributed in the message domain with a K is also universally distributed, uniformly distributed in K domain. In semantic security, what we say is that the probability of saying that C is coming from M0 versus M1 in perfect secrecy had to be 0. We now let's this to be a little bit more relaxed and say that it should be less than equal than some very small number epsilon. So essentially what has changed is that in perfect secrecy, this was absolute 0. In semantic security, we are changing this to a very small number epsilon, okay? So essentially we are saying that the probability of the attacker learning something from the message should be very, very small, but it's not 0. Okay, so first question, of course, is how much is small? Okay, and this is kind of usually what we call the security parameters. It depends on the algorithm that we use and the size of the key and message that we use. Usually, for example, we use numbers such as 1 over 2 to the power of 256. In some cases, even smaller numbers. So we are talking about really, really small numbers. Okay, we're not talking about like 1% or 100%. We're talking about 100,000ths of a percent or something like that. It should be very, very small. And again, there's a trade-off between the size of the key size of the message, and how small this is. There's usually standards for various different systems, including military systems and all, but this number is very, very small, okay? So how does this achieve improvement? I'm not going to show you the proof, but there are proofs that shows that semantic security can achieve OTP with K much smaller than M if we can somehow stretch the key. So in other words, we can use the same idea as OTP, which was basically M XORed with K. The difference is in semantic security, we start with the small k called seed. We stretch it to K, and then we apply this to M XOR K and get our ciphertext, okay? This S is much, much smaller than the key, and of course, key is equal to size of the M. And we can achieve semantic security. In other words, what I get from the C, M1 and M1 and M2, the probability of these two being similar is very, very small. If the algorithm that I use to kind of stretch this S, this C to the K, is one particular algorithm that we're going to talk about later, which basically makes this K pseudo-random looking. So what we need to do, essentially, the idea here is that I don't want to use a large K. Instead, I'm going to use a very small K, which we call seed. I'm going to find a way to kind of generate the large K, which we call stretching. If this large K is random looking, which is kind of similar to the original K that we had, then if I apply the same one-time pad and gets the ciphertext, this ciphertext is secure in terms of semantic security, okay? So basically, I'm reducing the problem of one-time pad to an algorithm that takes a small s and kind of stretch it. And the nice thing about this is now I can go with, let's say, if I want to create a 1 GB size, K, I don't need to store this. Maybe I can just go with 1 kilobyte of seed, then have an algorithm which we usually show it as G. I can generate G of S, and then I can create that 1 GB. So the rest is just, I'm really just storing 1 kilobyte, then I'm generating 1 GB of data, random looking data. What this G is, I'm going to talk about it later. But this just know that there is some form of algorithm. Important thing is that it's not any arbitrary algorithm. So for example, it's not like, I repeat S like 1 million times and that gives me K and this is a secure K. It has to be a particular algorithm that follows a specific criteria that I'm going to talk about later. Okay, but just know that there are these certain stretching algorithms that just stretch the seed to the K, and then I'm going to apply one time. Okay, and what has changed here is that difference between this and regular perfect secrecy is that here we leaking something, but that something is very, very small. Okay, so this is not as good as perfect secrecy, but it's good enough for our system. Any questions?
What is the S again? Because sometimes yeah, what is the S?
S is the seeds. It's the smaller K, okay? So remember for OTP, okay, I need my message XOR with K, okay? And the size of M and size of K should be the same, okay? So what I'm doing here is that now I'm saying that instead of using K, I'm going to use S, which is much, much smaller than K. So for example, if this is 1 GB, this is 1 kilobyte. And then I'm going to feed this S to this generator function G of S, and the output of this is K.
Thank
Okay?
you.
One quick thing before moving on is essentially there's this notion of message recovery attack, and semantic security is easier to describe with message recovery attack. So let's actually do that. So essentially the idea of message recovery attack is that if I have a message, okay, if I have a domain of messages, I have m different messages, 1,000 different messages, I just randomly pick a message m prime and encrypt it and send it to the attacker. The probability of the attacker can guess what is this message should be 1 over m. In other words, the attacker cannot tell the difference between any message that I'm sending to them. And of course, this should be smaller than some epsilon. So there is some, I mean, there is some probability that the attacker can guess this, but this guess should be very, like this probability should be very small. Okay. And then how does this relevant to semantic security and probability of E and C? There's some math behind this that shows that how these two are relevant. But generally, again, just keep in mind that what we're trying to achieve here is that if I see C, I should not be able to tell anything about M. The ability of the attacker to tell the difference between different messages should be very small. That's what we are trying to achieve. And the interesting thing about semantic security is that you can also talk about this in terms of bits. And what we can say about semantic security is that the attacker cannot even discover individual bits. In other words, for example, the attacker cannot tell whether this value is even or odd. The attackers cannot tell the difference between the most significant bit or least significant bit or any bit in between. In other words, not only the messages look random, but individual bits within the message also look random. Excuse me. And that's the importance of having a secure encryption mechanism. If your encryption mechanism somehow, for example, leaks a particular bit all the time, so for example, this bit is always 0 or this bit always 1, then this is not a secure encryption mechanism. So it should be within the individual bits as well. Okay. So now that we kind of know that what are we looking after? So essentially we want to have one-time pad. We really like one-time pads, very simple. Perfect secrecy was difficult because you have a key that is very large. So we introduced semantic security one-time pad, which essentially the idea was, let's not have a big key. Let's have a small key, but let's stretch the small key to a bigger key. And this way we're going to have a semantically secure one-time pad. So how do we stretch that? In order to do the stretching, we're going to have what we call stream ciphers. Okay. So stream ciphers are these spatial algorithms that take a small seed S and somehow stretch it to some K key and then apply the one-time pad afterwards. Okay. As I said, under certain conditions, which include how we create this seed. Okay. And how we stretch it, then we're going to achieve semantic security. As I said, not all the seeds and not all the stretching algorithms are secure algorithms. So what are those? So let me actually give you a little bit more formal definition of stream ciphers, and then later I'm going to describe the security criteria. So here's what we're going to achieve, and this kind of also answered the question that Isha asked. So the seed S is a vector of zeros and ones of size lowercase l, okay? Our message domain and ciphertext domain are our size of capital L, uppercase L. And the big thing here is that lowercase l is much smaller than uppercase L, okay? Both of them are vectors, but S is much smaller in size than M and C, okay? So under the stream cipher encryption, what we're going to have is that our encryption going to take S and M. Keep in mind that here that we are not sending K. There's no K anymore. There's only S. So the encryption algorithm takes S and M. What it does is that it sends S to this generator function G of S. Then this G of S is going to generate a very long message, so very long vector. Then you can actually bitwise XOR that with M, and that would be your ciphertext. The encryption is exactly the same. So you send S and C, you get G of S in order to create that same long vector. You XOR it with C, and they're going to get your message N. Okay? So the difference between this and regular one-time pad is that in regular one-time pad, you had key, K, and M. Here you have S, which is G of S, in other words, is equal to K. Okay? That's the only difference. Okay? So this G of S, what is the criteria for this G of S to be secure? The main thing is that G of S should be indistinguishable from any random string R. Okay? If that's the case, then we call this system a secure stream cipher system. So essentially, if I take a seed and generate a sequence R, this sequence should be indistinguishable from just any random sequence of that size. If that's the case, then we're going to have a secure system. If that's the case, we usually call G of S a pseudo-random generator, or PRG. PRGs are this class of functions that takes an input S, this takes seeds, it stretch it to a longer sequence, and that longer sequence looks random. If we have that, we have a secure PRG, or secure pseudo-random generators. Okay? As I said before, not each stretching function is a secure one. How do we know that we have a stream cipher that is secure? There is a series of standard statistical tests. Remember, I told you that the sequence should look random and should be indistinguishable from a random sequence. So there are a sequence of tests, a statistical tests that generate a real random sequence and a random sequence generated by GFS. Compare these two. If there is enough similarity, then we say that this is a secure stream cipher. Who designed those standards, statistical tests and all? There's usually working groups. There is National Institute of Standards in US that creates these sort of standard tests, okay? So it's not like, tomorrow we can wake up and design a stream cipher. It has to go through a very, very rigorous process in order to be used as a secure stream cipher. So it's not like, oh, okay, I'll take like the first bit and then I repeat it twice and then I do this and do that, and then suddenly I'm going to have a stream cipher, okay? So what are the popular stream ciphers? There are various different ones. There's the ones that commonly used these days are Salsa and Cha-Cha. The names are a little bit interesting as well. There's also Seal. Used to be RC4, the most popular stream cipher. Unfortunately, RC4 later became not secure anymore because there were vulnerability discovered. And one thing that you will realize is that these stream ciphers, since they are not based on hard theories, they're not like, based on grounded mathematics for security. They're just qualitative numbers. So that's why it's only statistical sets. So sometimes in someday in future, Salsa might not be secure as well, but at least for now, it's a secure system. Okay. So going back to the issues of OTP, stream ciphers fix the first problem. Essentially, now with stream ciphers, I don't need to store a large key. I store a very, very small key. I have a stream cipher algorithm, for example, Salsa or Cha-Cha. Then I can stretch this, and then I'm going to have the OTP, regular OTP that I can just XOR, and then boom, I'm going to have my encryption. The encryption is the same thing, okay? So this problem is solved. Let's talk about the second problem, the two-time pad or many-time pad. How do we fix this problem? And remember, the problem was that if I encrypt the same thing using one-time pad, I'm going to keep getting the same number over and over again. And I don't want that because the adversary will see my pattern and will discover that I'm keep sending the same message. So I'm basically leaking some information, which I shouldn't. So how do we do that? So basically the idea here is that we need to have some form of a different key. If the message is the same, the only thing in this function that we have is a different key, okay? But keep in mind that keep changing the key might be very, very challenging things, because remember, for decryption, we also need the same key. So for every single message, if I need to change the key, I need to somehow also tell the decryptor, the receiver of this message, that I changed the key, and they also need to figure that out. So that's a very challenging problem. So generally, just keep changing the key is not a feasible option. Instead, what do we do? What do we do? We go with what we call a probabilistic cipher, which essentially the idea is that we're gonna have some changes in the system such that by changing some parameters in my cipher, I'm gonna get a different ciphertext. And when I get that different ciphertext for the same message, if the receiver and sender both agree on some protocol to generate this different, inputs to the systems, then they can actually decrypt the system successfully. Let me give you an example so that you can understand this. So essentially, the idea of a stream cipher is this, that I'm going to have my seed or my key K, okay? This is usually what we show so far as S. The stream cipher is this G of S, okay? But if I just have the S, then G of S is going to generate this key stream. And then I'm going to do the plain text XOR with this. I'm going to get the ciphertext. If my S stays the same, if my plain text stays the same, the ciphertext stays the same. So what's the trick? The trick is introducing this additional thing called nonce, okay? Nonce means a number that is used only once, okay? So basically the idea is that I'm going to use a number and I'm going to use this number only once. So essentially I'm going to change this number every time I'm going to encrypt a message. Then this G of S, instead of like then using G of S, I'm going to use G of S of N. Essentially generating this key would be now a function of two things. Function of S, which is a secret value that nobody knows about. And this N that is just a counter that could be shared publicly actually. And then what I'm going to do is that based on this, I'm going to generate this sequence. Now this sequence is function of both. So next time, even if I'm having the same message and having, excuse me, having the same secret, I'm going to change this nonce to some other number. Remember, this nonce has to be supposed to only use once. So if I want to have, for example, if I have the yes message, the first time I'm going to use, for example, S and number 1, and I'm going to create some K, and I'm going to one time pad this and then get the ciphertext 1. The next time I'm going to have yes, I'm going to have S, and this time I'm going to have a different number. Let's say number 2. I'm going to have the different KK prime. Then I'm going to XOR these two guys, and this time I'm going to get C2. Interesting here is that the message is the same. The secret value, the seed is the same. The algorithm is the same. The only thing that's been changed is this number 1 and number 2. And then I can then generate different values. The beauty of this is that then I can share this nonce publicly with the receiver. I don't need to, this doesn't need to be secret because the secret part is this S. This nonce value could be public. I can also have some form of a counter-based system, which, for example, saying that, okay, generally the sender and receiver can agree on the counter. Let's say the counter starts at number 100. For every message, both of them counts up. So essentially for every message that's been received, we change this number and then we're going to use this counter as my nonce. Okay. And this way, again, if I keep encrypting the same message, I'm going to see a different ciphertext. The adversary has no idea whether I'm encrypting the same message and the results is different because the cipher, the nonce is different, or whether I'm doing a different message and just the ciphertext looks random. Because from the adversary point of view, they only see the C1 and C2, and in both cases, it looks very random, and they're not the same. Could be coming from yeses, could be coming from, for example, this time I'm encrypting now. Okay, so this is where the semantic security on the chosen plain text coming to the effect. Even if the attacker knows the plain text, still they cannot differentiate between these two because I'm changing my nonce. Any questions here? Jacob.
Yes, that question. So the goal is never to use the same nonce twice, right? And if you do use the same nonce twice, then you're compromising the security of the whole algorithm.
Exactly.
Okay.
Yep. Because then you might have the same message being twice. So you never use a nonce twice.
I'm a little confused on why necessarily if the attacker sees the same message encrypted multiple times, it makes a difference? Because wouldn't it be enough to just see it once if he knows it's the same key?
Wouldn't be enough. Can you repeat the second part of your question? Wouldn't be enough if he knows the same key. What do you
Like if
mean?
the same seed was being used every time and there's no nonce, wouldn't just one or a few messages be enough to figure out the encryption? Unless if I'm misunderstanding.
So the idea of the not repeating is this, that let's say I don't know what this message is, okay? So let's see, I see this, okay? I don't know which one is yes and which one is no, for example, but let's say I know this one is yes and one is no, okay? So if I see these patterns, I know that there are either three yeses and one no's, and there are three no's and one yeses, okay? And let's say there is some additional metadata that somehow I know that the probability of yeses is more than no's, okay? So based on that, I can say that, for example, oh, this is actually the correct answer. Uh, uh, this is kind of like things, or another thing that could happen is that, for example, I can correlate this answer with some knowledge that I have before about the system. So for example, in the past, I saw that you did C1. Let's say, for example, I see fire in Los Angeles, and so I saw, looking at the messages, I see lots of C1, C1, C1s. Probably this means that C1 is fire or something similar to that. And in future, if I see C1 again and again and again, that means that same thing is happening in another place. So essentially, what this is trying to do is that any sort of repeating pattern should not be exposed to the adversary. If I do even the same thing over and over and over again, should always result into the different message. Actually, the funny thing about this, interesting thing about this is that I told you about Enigma machine and World War II. I don't know how many of you have watched this movie called Imitation Games. It's a very interesting movie. I would definitely recommend you. But there's this guy, very famous guy called Alan Turing, which is also a very famous scientist. Yeah, someone will love that movie. So Alan Turing is this very famous scientist, which actually now all these awards that prominent computer scientists achieve is Turing Award. His name is based on his. So what he did and his team does is actually this, that they look into lots of kind of letters coming from the Nazis. And what they found is that all of the letters kind of starts with the same sentence. At the time, they didn't understand what that sentence is, but then eventually they figure out that this is kind of like something to the Nazis. So they figure out this kind of like something like Heil Hitler, something like that. So they saw the same thing and they understood that this is actually the same sentence over and over. They then kind of use this in order to break the encryption algorithm. So again, what you need to do in a secure system is you should not repeat the same ciphertext, same message and ciphertext over and over again. Otherwise, you're basically leaking the pattern of your system. Does that make sense?
Yes, thank you.
Mm-hmm. Someone asked, could you clarify why we can safely announce nonce to the public? Because nonce is not part of this. So essentially, this system remains secure if you know the nonce, because you still don't know the S. So at this point, if the adversary knows the nonce, they cannot still recover the secret key. That's the key in this system, because nonce has nothing to do with the secret key. Okay, let me give you an example. This is actually courtesy of ChatGPT. I asked it to give me like a simple examples for you guys to follow. Actually, you're gonna do your project, and in the project, you're gonna do it yourself as well. But let me give you just sometimes actually an example helps people to understand this. So let's say I have a message hello, HELLO. And then let's say my seed, my secret key, my initial data secret value is 10101101, 8 bits. Okay. So I want to have some form of a stream cipher to kind of encrypt this. Okay. So let's say the first step I will do is that I generate the binary values, the bytes for each of these characters. So what I'm going to get is, I'm going to get the ASCII values, and I'm going to translate this ASCII value to the binary value. That's all I'm doing here. And I'm going to get 5 bytes basically. Okay, so this is 5 bytes. My secret key is 1 byte. Okay. And what I want to do is that I want to apply one-time pad. First thing you will see is that I cannot just XOR this with this because that's not the same size. So I need to somehow stretch this. How do I stretch this? So basically, I'm going to use some form of a stretching function, some form of a pseudo-random generator. Okay. I asked ChatGPT to give me an insecure one. So this is what it's been given based on a just linear feedback shift registers. This is not secure and you should never use it. You actually should use a secure pseudo-random function such as cha-cha and so on. But linear feedback shift register, basically all it does is it shifts the bits. So basically this is your original key. As you can see here, what it does is just shift things to the left and right, and it generates this longer sequence of bits for your key. Okay, so basically this is all you get from this. Then what it does is that it encrypts this with this. This example I'm giving you, it doesn't use any nonce. But now you can, for example, use nonce in this linear feedback shift register. So if I use nonce, what I'm going to have is, if, for example, the nonce is 0, I'm going to get this. If nonce, let's say, is 1, then I'm going to shift this by another bit to the right, and so on and so forth. So think about the nonce in this particular example with the value of the nonce. Basically it's the amount of bits I'm going to shift this or add to this and so on and so forth. So essentially that makes this key different each time. Remember, this is not secure, which means that the nonce is not going to be creating a uniformly distributed random looking key. That's why if I, for example, just shift everything by 1 bit, this is not going to be a secure system. But just imagine that this is, and as I said, in real system, this is. Once I have this sequence of bits, then I'm going to just basically XOR these two numbers together, and that will be my ciphertext, okay? Giving you an example of the first byte. This is your input, this is your key, this would be your ciphertext, and then this is the whole thing if you want to check and look at it. And this would be your ciphertext, eventual ciphertext. If you want to look at the hex version of the ciphertext, that's here. So basically, that's kind of the idea. As I said, real systems doesn't generate the bit like this. If you're interested, if you just Google cha-cha 20, cha-cha 20, there is a very nice kind of graph that shows how the key has been generated. But that's basic idea of how we do create the key bits. Any questions here? Perfect. So we fixed both problems, the one-time pad and two-time pad, many-time pad. And the other question is this enough? And that's all we need. In many cases, it is. Actually, stream ciphers is regularly used in many systems. So encryption, decryption, you technically are perfectly fine with having stream ciphers the way that I describe it. And of course, you just need to make sure that the generation function is a secure function, not an arbitrary function like the one that I'm showing you here. But there is also another very famous group of encryption functions called block ciphers. The idea of block cipher is, I'm going to very briefly talk about it and then I'm going to finish this class. The idea of block cipher is this, that I don't want to necessarily have one-time pad and going through bit by bit to generate the ciphertext. What I do want to do is somehow something that I can just create a big block of inputs, sending it to this block cipher, and then gets the result out. Okay. Why this is helpful? Because this is usually significantly faster, because instead of going through bit by bit, I'm gonna basically works on chunks. Okay. And this creates much faster computation, because then I can take like, 512 chunks in one operation is gonna get and encrypt the entire 512. Versus for stream ciphers, I need to kind of generate the key bit by bit and then gets another bit and another bit, so which is usually much slower. So usually block ciphers are significantly faster than stream ciphers as a result of this. Okay. So how do we create this block ciphers? The fundamentals are very different. It's no longer one-time pad, it's no longer stretching functions. What it is, let me give you this very simple examples, and I'm going to let you guys go. We're going to use, instead of what we call pseudo-random generator, PRGs, which we use for stream ciphers, now we're going to use what we call pseudo-random permutations, or PRPs, okay? So what is a PRP? PRP is a one-to-one function that maps a domain into its own, okay? So essentially, if I have again, credits to ChatGPT. Let's say my domain is 0, 1, 2, 3. Okay. So essentially a PRP, this is not a secure PRP, but a PRP is like this, that if key is 0, then I'm going to map everything to itself. We call this identity permutation. If key is 1, we're going to have, let's say, a shift permission. So for example, 0 is mapped to 1, 1 is mapped to 2, and so on. If key is equal to 2, 0 is mapped to 2, 1 is mapped to 3, and so on. If key is 3, 0 is mapped to 3, and so on and so forth. Okay? This is what we call a pseudo-random permutation. Based on the key, I'm going to have a different permutation. So if key is 0, this is my permutation. If key is 1, this is my permutation, and so on and so forth. So if I want to encrypt based on this, I'm basically going to do this way. So if my input is X and my key is 2, the permutation of P2 and 1 is 3, because, again, key 2, 1 is mapped to 3. So this way, I'm going to just generate a new permutation. And now think about a very large domain. What I can do is that I quickly can just find the new permutations and map it to that permutation, and I'm going to get my encryption. So a block cipher is kind of like this. Of course, there are lots of details that I need to describe to make this secure, but the general idea is that I can just, based on the key, find the new mapping, and that mapping would be my encryption. As long as this is random looking similar to what we had for one-time pad, we're going to achieve semantic security, similar guarantees that we achieve in PRPs and stream ciphers. Okay. So we're going to discuss this, and we're going to explain what is called AES, which is very, very famous block cipher, which probably most of you are familiar with. Any final questions before I let you guys go? Otherwise, I'm going to see you guys, same link on Zoom on Wednesday.
Thank you.
Yep.
Thank you.
Thanks.